Hi everyone, welcome to the Chemical Engineering Process Design learning videos with Aspen Plus software. This is our third video lesson. This video lesson provides you knowledge and skills on using Aspen Plus software to simulate material and energy balance problems, using the calculator function in Aspen Plus software to perform customized calculations, and simulating reactions with fractional conversion using our Stoic reactor model in Aspen Plus software. Let's take an example material and energy balance problem and first see how we can use the calculator function in Aspen Plus software to perform a calculation. Read the example problem carefully. For an acid pretreatment process, a 50 weight % diluted sulfuric acid solution in water is required, but the available acid solution is 98 mole % sulfuric in water. We need to find how much water should be mixed with 100 kilograms per hour of initial acid solution. We shall consider the room conditions 30 degrees C temperature and 1 atm pressure. So as illustrated from the figure, we need to find the mass flow rate of water that should be mixed with 100 kilograms per hour of 98 mole % sulfuric acid in order to obtain a 50 weight % diluted sulfuric acid solution. Let's see the manual solution for this problem before continuing for the simulation. Let's take the water amount to be mixed as alpha kilograms per hour. When we apply the material balance, we shall consider that there is no accumulation inside the mixer. Therefore, the total mass flow into the system should be equal to the total mass flow out of the system. If we apply the material balance for sulfuric acid, we get the final answer for the required mass flow rate of water as 99.253 kilograms per hour. Now, let's simulate this problem in Aspen Plus software and check whether the simulation results approximates to the manual calculation result. Create a new simulation using the blank simulation option. Under the components, specify sulfuric acid and water. You can directly enter H2SO4 and water. After specifying the components, go to Methods, Specifications and Global Sheet. Set the property method to be NRTL, which is abbreviated from Non-Random to Liquid Property Method. Now, we have correctly specified the properties of our problem. So click on the Simulation tab to model the system related to the example problem. Select the mixer from the model library and place in the flow sheeting area. Select material stream and connect two feed streams to the mixer. Let's rename our feed streams as H2SO4 and water for easy identification. Then, connect a product stream from the mixer. Let's name it as product. Now we have completed the flow sheet relevant to our problem. First, we enter the input data for water stream. Enter the temperature as 30 degrees C and pressure as 1 atm. For the water mass flow rate, enter some value first. Also, enter the mass fraction of water as 1. Our goal is to find the real flow rate using the calculator function. So let's enter 50 kilograms per hour as the initial water mass flow rate. Thereafter, enter the acid feed stream input data. 30 degrees C temperature, 1 atm pressure, and the total mass flow rate as 100 kilograms per hour. Set mole fraction as the composition and enter 0.98 for H2SO4 and 0.02 for water. After completing the input streams data, go to mixer block input data. The pressure has been marked as 0 by default. This means the pressure drop in the mixer is 0. Our problem also doesn't have any pressure drop in the mixer. Therefore, let's keep it as it is. Since all the input data have been entered, click Run the simulation. We can see that the simulation status shows that the results are available. But we need to find the water mass flow rate from the simulation. So, go to the flowsheeting option tab in the navigation pane and first expand it. We can see that the calculator function is available under there. Select calculator and click New. Before entering the calculator function, let's simplify our problem further. Previously, we performed the manual calculation following the general material balance relationship. If we write the material balance in equation mode, we can write that the mass of H2SO4 in the feed is 0.5 times of total product mass flow rate. Let's symbolize mass of H2SO4 in the feed as M sub H2SO4. And let's symbolize total product mass flow rate as W sub product. The overall mass balance gives us another equation, that is W sub product equals to feed mass flow rate of H2SO4 solution plus feed mass flow rate of water. Let's symbolize feed mass flow rate of H2SO4 solution as W sub H2SO4 and feed mass flow rate of water as W sub water. Finally, combining these two equations, we can simplify the relationship into W sub water equals to M sub H2SO4 divided by 0.5 minus W sub H2SO4. We will enter this equation into Aspen calculator function. Let's go back to the simulation. In the Define tab of calculator, we have to specify the variables. Click New and name the variable. There are 3 variables to be entered. The first variable is W sub water, which symbolizes the feed mass flow rate of water. After typing the variable name as W water, click OK. Mark the streams option as this is a variable related to a stream. Then select the type of the variable as a stream variable. The corresponding stream is water. Substream has been marked as mixed by default. Select the variable as mass flow and the units as kilograms per hour. Since water flow should be defined based on other variables, mark this variable as an export variable. The second variable is the mass flow of H2SO4 in the feed acid solution. We symbolize it by M sub H2SO4. Mark the option as streams and select the type as mass flow and select the stream as the feed H2SO4 solution. Then select the component as H2SO4. Since mass flow of H2SO4 in the feed is an independent variable, mark it as an import variable. The third variable is the mass flow rate of feed H2SO4 solution. Let's name it as WH2SO4. Mark the streams as the option and select the stream variable as the type. The corresponding stream is H2SO4 feed stream and the variable is mass flow. Set the units as kilograms per hour similar to others. And this is also an import variable. After entering these three variables, go to the Calculate tab. The calculator functions can be entered by Fortran scripts or using Microsoft Excel. We shall select Excel as the calculation method as it is much easier than handling Fortran scripts. Then click on Open Excel spreadsheet. We can create a comprehensive Excel sheet for calculations in Aspen Plus. Let's type as mass flow of H2SO4 in the feed solution. The next row as H2SO4 mass fraction in the diluted product solution. Then total mass flow of feed H2SO4 solution. Finally, the mass flow of water. The corresponding cells for each variable can be marked by using previously specified variables. Go to Add Int tab in Excel sheet. We can see the three variables there. Click the next column to mass flow of H2SO4 in the feed solution row and select M sub H2SO4 there. Type the H2SO4 mass fraction in the diluted product solution as 0.5. Select WH2SO4 variable for total mass flow of feed H2SO4 solution. Finally, set the equation for mass flow of water as mass flow of H2SO4 in the feed solution divided by 0.5 minus total mass flow of feed H2SO4 solution. Now, close the Excel spreadsheet. Then run the simulation by clicking Run button. The results is shown in the space of calculator function. We can see that the simulation results approximates to manual calculation result. The advantage is we can perform complex calculations using this way of simulation when manual calculations are quite difficult. Let's continue the same simulation to solve an extended problem with adding a reactor to this system. First, read the problem carefully. After the pretreatment process, the outgoing acid solution should be neutralized by reacting with a 112 kilograms per hour of 80 weight% calcium hydroxide aqueous solution. We have to find the gypsum amount generated in kilograms per hour after complete acid neutralization at 60 degrees C and 1 atm. You can see the reaction between H2SO4 and calcium hydroxide on the screen. The stoichiometrically balanced reaction is equimolar. Let's see the manual solution for this problem. First, we need to find out what is the limiting reactant of this reaction. The calculation for maximum extent of reaction indicates that H2SO4 is the limiting reactant and 1.0166 kilomole of H2SO4 reacts with calcium hydroxide for complete neutralization. Therefore, we obtain the final calculation result for the gypsum amount generated as 174.86 kilograms per hour. Now let's go back to our simulation and proceed it for this neutralization reaction part. First, we should specify the new components. So go to Properties workspace and add calcium hydroxide and gypsum to the component list. We shall use the same property method as previous. Then go to the simulation workspace. Select R Stoic reactor model from the model library and place in the flowsheet. Rename the block as R-Neut to symbolize the neutralization reactor. We need to connect the product stream of mixer as a feed to this reactor. To do that, right-click on the product stream from the mixer and select Reconnect Destination option. Then connect as a feed to the reactor. Also connect a new feed stream to the reactor for calcium hydroxide input. Let's rename this feed stream as calcium hydroxide. Also draw the product stream from the reactor and rename it as gypsum. Click Next button and enter the input data for the calcium hydroxide stream. Enter 30 degrees Celsius as the temperature, 1 atm as the pressure, and 112 kilograms per hour as the total mass flow rate. Select mass fraction as the composition type and enter 0.8 for calcium hydroxide and 0.2 for water. Go to the reactor setup specification. Specify the temperature as 60 degrees Celsius and the pressure as 1 atm. Mark the valid phases as liquid only. Then go to the Reactions tab to enter the reaction. Click New. Select H2SO4 and calcium hydroxide as reactants and gypsum as the product. Also enter the stoichiometric coefficients of the balance reaction. For this reaction, all of them are 1. Enter the fractional conversion as 1 of the component of H2SO4. Click the Next button and run the simulation. When we use Next button, we can see any errors quickly as the control panel automatically opens. We can see that there are no errors in our simulation and the simulation status shows that the results are available. Go to the reactor block stream results. At there, we can observe that the simulation results give us the gypsum generated in the reactor product is approximate to the manual calculation result. Therefore, we can use simulation for more complex systems when the manual calculations are quite difficult. As a summary, what we learned in this lesson are as follows. Simulations in Aspen Plus help easy material and energy balance for complex systems. Calculator function can be used when additional calculations are required. The R-Stoic model is useful for quick simulations of reactors with fractional conversion. Please watch our next video lesson about batch reactor design using Aspen Plus software. Until we meet with our next lesson, have a nice day and goodbye.